Have you ever stopped to think about how we actually talk to a database? One with millions of records? Well, today, we're going to pull back the curtain on the theory behind it all and see how it connects directly to the language we use every day, SQL. So just imagine this for a second. You're sitting in front of a massive database. We're talking millions, maybe even billions of rows of data. It's like an ocean. So how do you dip in a net and pull out the exact piece of information you're looking for without getting everything else? That right there, that is the core problem that query languages were invented to solve. And when it comes to asking for that data, there are really two big picture ways to think about it. The first one is procedural. This is where you give the database a very specific step-by-step set of instructions. Then you've got the non-procedural way, where you don't care about the steps. You just describe what you want the final answer to look like and let the database figure it out. Okay, let's start with that first approach, the procedural one, which is called relational algebra. Honestly, the easiest way to think about this is like you're following a recipe. You're telling the database, okay, first chop the onions, then saute the garlic. You're giving it a precise set of instructions to get the final dish, or, data. So the first ingredient in our data recipe is the select operator. You'll see it represented by the Greek letter sigma. This is our main tool for filtering. It goes through a table and picks out entire rows that match whatever condition you give it. Think of it like looking through a huge pile of Legos and pulling out only the red ones. Let's look at a super simple example to make this real. Here's a table of employees. We've got their names, departments, and of course, their salaries. Our mission is to find everybody who makes more than 3,000. And boom, here's what we get after we apply our select operator. The operation basically scanned the whole table and handed us back a new table that only has the employees who match our condition. The key thing to remember here is that sigma filters horizontally. It finds the rows you want. But what if we don't need all of that information for each employee? That brings us to our next ingredient, the project operator, or P. And this is the perfect counterpart to select. While select picks rows, project picks columns. It lets you slice your data vertically, keeping only the attributes you actually care about. So let's build on what we just did. We take that table we already filtered, and now we apply the project operator to it, asking for just the name and salary. And look what we get. Same employees, but now we're only seeing the columns we specifically asked for. We've just vertically sliced our data. Now, select and project are kind of the stars of the show, but they're part of a whole team. Relational algebra also gives us tools to combine tables. The big one is the cross product, which smashes two tables together to make every single possible combination of their rows. You've also got union and set difference. With just these basic tools, you can build almost any data recipe imaginable. Okay, the basics are great, but what happens when you run into a really tricky question? For example, how would you find students who are enrolled in every single course the university offers? A for-all question like this is actually really hard to answer with just the basic operators we've seen. And that's where a special, more advanced tool comes into play, the division operator. It was literally designed to answer these for-all types of questions. So for our problem, you could take the big table of all student enrollments and you divide it by the table of all available courses. What you get back is a neat little list of just the students who are linked to every single one of those courses. It's a really powerful tool for a very specific job. All right, so that was the recipe approach. Now I want you to completely switch gears with me. We're going to look at that other philosophy, the non-procedural one. Relational calculus. If algebra is the detailed recipe, then calculus is just the wish list. You're not telling the chef how to cook, you're just describing the meal you want to eat. And this slide really nails the difference. Relational algebra is procedural. It's all about the how. You are defining the exact sequence of steps. Relational calculus, on the other hand, is declarative. It's all about the what. You just describe the properties of the data you want, and you let the system worry about the how. And the way you write it is actually beautiful in its simplicity. A query looks just like this. And all it's saying is, hey, database, give me the set of all rows, we'll call each one T for short, where some condition that I'm about to specify is true. That's it. You're not saying how to find them, just what they look like. So now we've got these two really powerful but really different theoretical ideas. We have the step-by-step recipe of algebra, and we have the descriptive wish list of calculus. So where does that leave us in the real world? Well, it leads us straight to SQL, which, as it turns out, is a brilliant combination of both. Okay, and here it is. This is the big aha moment. The SQL that you write all the time is a direct practical application of relational algebra. Your SQL select clause, that's just the project operator, pi. Your where clause, that's the select operator, sigma. And the from clause when you're joining tables, under the hood, it's based on that cross product operator. It's all connected. So here's the absolute key takeaway. When you write a SQL query, you're using that declarative wish list style that comes from relational calculus. You just describe what you want. But when the database actually goes to get the data, it translates your query into a logical recipe, a plan of action based on relational algebra. So with SQL, we really get the best of both worlds. You know, understanding this deep connection isn't just for acing a test. It actually makes solving some of the trickier, real-world SQL puzzles a whole lot easier. Let's look at a classic one. Here is a question that trips up almost everyone when they're learning SQL. We know that the where clause is for filtering individual rows. But what if you need to filter based on a property of an entire group of rows? Like, say, you want to find only the departments where the average salary is over 5,000? Well, the answer comes directly from that procedural recipe-like logic of how SQL works. First, the where clause runs and filters out individual rows. Then, after that, the group by clause takes all the rows that are left and bundles them into groups. And only then, at the very end, does the having clause come in to filter those newly created groups. That's why you can't use where for this. When where is doing its job, the groups don't even exist yet. And this all brings us to a really deep fundamental truth in computer science, which is that relational algebra has the same expressive power as safe relational calculus. What that really means is anything you can describe with the wish list approach, you can also build step by step with the recipe approach. They are essentially two sides of the very same, very powerful coin.
So I'll leave you with this final thought. The next time you sit down to write a SQL query, ask yourself, are you thinking like the chef who's building the recipe step by step, or are you thinking like the customer who's just writing down their wish list? Realizing that you're actually doing both at the same time, well, that's the secret to truly mastering the language of data.